Uh, Good afternoon, everybody, and thank you for being here. I try to make it short, quick, and not to let you to fall asleep. Uh, let's start with an important question. What is an active black hole? An active black hole is very much similar to a T-Rex. Yes, a T-Rex. It's super angry. It has a desire to eat everything close to it. It's huge. It's super massive. And thanks God, it has these short hands. So it can just grab things which are in the vicinity, not far away. But to be fair, an active black hole is prettier than a T-Rex. It's something like this. Actually, black hole is here, but it is using its strong short hands to grab everything around it and just swallow it. That's why matter is accreting around the black hole and falling into it. This matter is accreting super fast, very fast, with orbital velocities of like 30,000 kilometers per second. Which means it's very, very, very hot and it has emission. Anything super hot has emission. And this emission is super important to us. That's something that we measure and then based on which we can determine the mass of black hole. How? We mainly use Hubble Space Telescope. You probably have heard about Hubble Space Telescope. Oh, I'm super sorry. I thought I'm loud enough. I can yell. So yeah. So, okay. Sorry. So we mainly use Hubble Space Telescope, but I also use 6 more famous space telescopes. Hubble watches the black hole for us, send the data to the tracking and data relay satellite, and that satellite sends the data to the Earth. And its final destination is the Space Telescope Science Institute, which is on Johns Hopkins campus in Baltimore, Maryland. They pay us here at UK to work on this data and try to analyze the data. This is how the very first image taken by Hubble Space Telescope is like. We use our softwares, our codes, our simulations, and we make it something like this: energy versus time, or energy versus frequency. Still, we cannot use it. It's very busy, it's noisy, it's dirty. Again, we work on it. A lot of human effort and time goes into previous images, and we finally get something like this. Simple energy versus wavelength, and all of these heights, all of these widths, the place of these peaks, all of them include a lot of information about the black hole. We care about them. We want something like this. Something else that I use a lot is a time delay. What time delay? Suppose this is the black hole and it has those emissions around it. There are 2 different ways to see the light coming toward us. First, we can just directly the light, which is this black line here. We call it line of sight emission or the continuum. We can see it. So whenever it gets more luminous, this light here will get more luminous. Or if it gets fainter, we see it fainter. That's normal, right? That's what we expect to see. Sometimes the light doesn't necessarily come toward us. It goes somewhere, strikes on some cloud in the neighborhood, and then comes toward us again. Again, we are looking at the same light, but with a time lag, because it had to go through this extra distance, right? I care about this distance. We measure this distance, and based on this distance, we can find the geometry of the black hole and the galaxy, which is including the black hole. I just want to emphasize on the time lag more. So this is the intensity of the light versus time. This is the one that comes directly toward us. Then the reflection, the emission one, is something like this, with general similar behavior, but with a time lag. So we measure this time lag, or we can just simply shift the reflection and match them. This is a fundamental rule of physics. This seems simple, but 40 years of black hole mass determination rely on this simple, very simple fact. This is the causal behavior of the nature. Now let's talk about this very famous galaxy, which includes a supermassive black hole, an active black hole. It's called, it's called NGC 5548. There is a black hole here. It's not that hot. It just 70,000 Fahrenheit. And it's super close. It's just 21 with 20 zeros miles away. We say California is far, but to us, weird astronomer, this is close. And it weighs like a tree with 38 zeros pounds. It is super massive. This is my favorite object. This was NASA's favorite object for 30 years until 2014, in which 100 astronomers from NASA and European Space Agency started watching this object because they wanted to see that correlation. They wanted to measure the time lag and then find the mass. This is the normal behavior. You can see the black is the continuum, and it nicely matches with the reflection. That's what we want to see. But starting from middle of the campaign, physics stopped working. Something weird happened. Emission line went on a holiday. We had no name for it, so we just called it holiday. So emission line stopped responding to the variation of the source. It didn't work for 70 days, and then it started working again. It was weird. I'm just saying it, but I got goosebumps because this is still weird because it means physics is not working, and it was the first time something like this was observed in the whole history of astronomy. People started working on it. They worked on it for 3 years. They couldn't find any answers, so they reached out Dr. Gary Fairlands here at UK. He is a super famous scientist who is well known for his great knowledge of photonization modeling and atomic physics. Plus, he is a developer of a code called Cloudy Code, which had been used by NASA for the last 30 years. And the Cloudy Code was developed here at UK. I was his new PhD student at the time. He told me, hey, Maryam, you can pick it up as your dissertation, as your research, but it's too risky. Already 100 astronomers couldn't do anything. So probably we cannot do anything after several years, and we have to start over again, doing something else. But if we can do it, it means we will be really famous in our field. And we have this great knowledge of atomic physics with which anybody else in the world has like us. He's really confident, and he must be because he's the best. And I can say, since I'm standing right here, not crying, not hiding, being a postdoc here, it means we did it. Astronomy is very different from any other field of science because we are sitting here in our offices and we are deciding about something far in the space. We cannot touch our object. We cannot sample it. We cannot see it. We cannot, oh my God, we cannot do anything about that. We can just use light, only light. And even this light is not pure light. It travels 300 million light years toward us. And there are a billion things between the source and us. So it's affected in any way that you can say. And still, that's the only thing that we have. What do? We run our codes. We make thousands line of codes. We do 100 simulations. We did everything we could. And we worked for 3 years, and we did it. We found out our nice, beautiful black hole is not alone there. There is a huge tornado of gas surrounding the black hole, this blue one here. Very hot, very ionized, affecting everything. There was no way to know that this tornado is there without our simulations. And now, not only we know it's there, but we know its properties. We know if it was there, it can be everywhere in the space. So we kind of affected the whole society, and we asked them to consider these tornadoes in all of the future studies. That's why NASA gave us more money. Actually, NASA gave UK a lot of money to hire me as a postdoc to continue my work on this project. And there were several press releases on this project. This is the one done by UK now at 2020. And right now we are working on another object with the same behavior and probably with the same tornado. Thank you.